In rocket science, specific impulse, or ISP, acts like gas mileage, measuring how efficiently an engine turns propellant into thrust. Standard kerosene engines hit a limit around 311 seconds. For decades, the space shuttle's hydrogen-oxygen mix held the record at 452 seconds. But in 1968, a team of engineers at Rocketdyne decided to ignore traditional constraints. They built an experimental tripropellant engine that reached a record of 542 seconds. Hitting that mathematical limit meant abandoning standard propellants entirely. Instead, they fueled their engine with some of the most reactive and corrosive substances on the periodic table. The pursuit of maximum thermodynamic efficiency forces a rigid trade-off. To reach this specific peak of performance, engineers had to move past conventional safety protocols. Pushing past that 452-second mark requires a chemical escalation. You have to find an oxidizer significantly more reactive than standard liquid oxygen. Their first substitution was liquid fluorine. Fluorine is an aggressive oxidizer that will strip electrons from almost anything it touches, including glass, asbestos, and solid concrete. For the fuel, they selected lithium for its energy density, but because lithium is solid at room temperature, it had to be heated to 300 degrees Celsius and injected into the engine as a corrosive, molten liquid. This diagram shows the final step. To hit that 542-second record, the engine injects cryogenic liquid hydrogen directly into the lithium and fluorine inferno. The heat from that reaction violently accelerates the much lighter hydrogen particles out the nozzle to generate maximum exhaust velocity. By combining aggressive oxidation, maximum energy density, and high-velocity exhaust, the team found the only known chemical pathway to push an engine's ISP past 500 seconds. Testing this required moving the operation to the Santa Susana Field Laboratory, a site with massive industrial test stands built directly into the Rocky Hills outside Los Angeles. The plumbing for the engine created a direct thermal conflict. Engineers had to route super-chilled, cryogenic liquid hydrogen lines mere meters away from tanks holding molten lithium at 300 degrees. When they finally fired the engine, the mixture ignited instantly on contact. The tests generated immense thrust, but the reaction frequently melted the experimental nozzles and plugged critical fuel lines. Furthermore, the combustion process exhausted a plume of hydrofluoric acid. This is a toxic vapor capable of dissolving the test stand's concrete and damaging human bone. Those firings proved the 542-second theoretical limit was reachable, but they also proved the hardware degradation and toxic exhaust were incompatible with operational spaceflight. So, if the tripropellant engine is mathematically the most efficient chemical rocket ever tested, why isn't it used for modern interplanetary missions? NASA investigated this in 1970, contracting the space division of Chrysler, to see if a tripropellant upper stage could adapt for heavy-lift rockets like the Saturn V. Despite incredible energy per kilogram, lithium's low density requires an exponentially larger fuel tank. This creates a cascading weight problem, as oversized tanks need thick thermal insulation and dedicated electrical heating systems to prevent freezing in space. Chrysler's study concluded that the weight of these heating and containment systems completely erased the payload advantages gained from the 542-second specific impulse. The tripropellant engine's legacy proves that in aerospace engineering, the limits of exploration aren't just dictated by thrust, but by the physical mass required to safely manage it.